As we've been doing for the majority of this chapter, we're going to look at things that we have learned previously in physics in a linear sense and make them rotational. This video focuses on Newton's second law and its rotational equivalent. So what is Newton's second law? Hopefully you answered that Newton's second law is that net force equals mass times acceleration. What is the rotational equivalent of net force? Well, that's net torque. What about the rotational equivalent of mass? We just learned that that was moment of inertia. And the rotational equivalent of linear acceleration is angular acceleration. So net torque equals I alpha. Net torque is the moment of inertia times the angular acceleration. Whatever the direction is of the angular acceleration, clockwise or counterclockwise, will be the direction of the net torque, and vice versa. So let's look at some problems that use this very important law. Starting out with example number 9, which is number 33. This example deals with a large grinding wheel. It tells us that its shape is a solid cylinder. It has a constant tangential force being applied to its edge, which causes the wheel to have a certain angular acceleration. Part A asks about the moment of inertia of the wheel. Well, we now have two ways of solving for moment of inertia. Our options are to look up the equation for the moment of inertia of a solid cylinder, or to use net torque equals I alpha. The equation for the moment of inertia for a solid cylinder is 1/2 mr squared. It doesn't matter if you use a capital M and R or a lowercase m and r. Well, based on the information I'm given, I know that I have a radius, but I'm not given a mass. As a matter of fact, if you look at part B, we're trying to solve for mass in part B. So clearly, going about the route of using I equals 1/2 mr squared is not a possibility to find the moment of inertia in part A. Instead, we'll have to look at the net torque equation. In this case, there's only one force producing a torque. Therefore, the net torque is simply equal to the applied force times the radius times sine theta. And that force times radius times sine theta is equal to I alpha. Well, we know what the applied force is. It tells you that it's applied to the rim, so the radius of the wheel is the same as the radius for the torque. We know the angle because we are told that it's a tangential force, and we're given the angular acceleration. So the moment of inertia is the applied force times the radius times sine theta divided by alpha. The applied force is given to us to be 250 newtons. The radius is 0.33 meters. Because this force is tangent to the curve, tangent to the circle, the angle between the radius vector and the force vector is 90 degrees. And the angular acceleration that is given to us is 0.94 radians per second squared. Plugging all those numbers into a calculator, you get that the moment of inertia is 87.77 kilogram meters squared. As previously mentioned, part B is asking us to find the mass. Now I can use the equation that I equals 1/2 mr squared. Solving for m, I find that m is 2 times I divided by r squared. I is the number I just calculated. R is 0.33 meters. As I plug these numbers in, I find that this grinding wheel has a mass of 1,611.86 kilograms. It's a large mass, but grinding wheels are typically very heavy. Lastly, in part C, we are asked to find the angular velocity after 5 seconds, assuming that this grinding wheel starts from rest. Doing this portion is actually a little bit of review. A review from chapter 7, where we use the equation omega final equals omega initial plus alpha times time. Omega initial is 0 because it starts from rest. So we'll use 0.94 as our angular acceleration times 5 seconds, which gives us a final angular velocity of 4.7 radians per second. Moving on to our next example, number 35 in your textbook. This deals with a person hanging from a rope that is wound around a cylinder. The cylinder is free to rotate, and the man falls under the force of gravity, but also with holding onto the rope. A wants to know what is his acceleration. Because gravity is acting on this man, and tension is acting on this man, his acceleration will not be the acceleration of gravity, 9.8 meters per second squared. These two forces will combine together to give him a smaller acceleration. To solve this problem, we're going to look at both net force and net torque equations. So let's first draw a picture of the situation so we have an idea of what's going on. So there's my cylinder. There's my coils of rope. And my man holding onto that coil of rope. Looking at the forces acting on the man, there are two forces acting on him. Tension is pulling him upward. Gravity is pulling downward. And those both equal mass times acceleration. In this case, the man is going to be accelerating downward, so his acceleration would be negative. I put the negative sign in there to indicate that. Next, let's look at a net torque equation. The only thing causing a torque on this cylinder is that tension force. So the net torque is tension times radius times sine theta. We know that that's equal to I alpha. We have two unknowns. Actually, looking at this, it looks like we have three unknowns, but we only have two equations. So clearly we need one more equation, because we don't know tension, we don't know acceleration, we don't know angular acceleration. The one other equation that we need is that angular acceleration is the linear acceleration divided by the radius. Three equations, three unknowns. We're good to continue on now. Keeping in mind what we're looking for, which is acceleration, and what we know. We know the mass of the cylinder. We know the diameter of the cylinder. We know the mass of the man. Based on this, I can calculate the moment of inertia. I know the radius, it's half the diameter. I can find the angle. I know the mass. Now it's important to remember that this mass right here is the mass of the man, because this is the net force acting on the man and the acceleration of the man. I can also calculate the force of gravity. So let's put this all together. The first thing that I'm going to do is substitute in this equation into there. So that I have tension times radius times sine theta equals IA divided by R. Now I only have two unknowns in that equation. I'm going to solve this equation for T, the tension, to plug it into the net force equation. T equals IA divided by R squared sine theta. Plugging that into the net force equation, I get IA divided by R squared sine theta minus mg. I'm choosing mg as plugging that in instead of fg. That's equal to negative ma. The next thing I'm going to do is plug in an equation for I. This is a solid cylinder, so I is 1/2 mr squared. It's important to keep the two m's different because this small m in this equation is mass of the man, but the m here is mass of the cylinder. So I'm going to choose to plug in a tall m, uppercase M there. Plugging that into this above equation, I have 1/2 capital M R squared A divided by R squared sine theta minus lowercase m times g equals negative lowercase m times A. Okay, well I notice the R squareds cancel each other out. The angle between the force and the radius is 90 degrees because that tension would be pulling tangential to that. The sine of 90 degrees is 1, so I'm going to cross that out so that I get rid of that. I'm left with 1/2 ma minus mg equals negative ma. I need to solve for a, so I'm going to get both terms with a on the same side of the equation. Then I'll factor the a out. And lastly, I'll divide both sides by 1/2 capital M plus lowercase m. So that a is mg divided by 1/2 capital M plus lowercase m. Now all I need to do is plug in numbers. The mass of the man, which is what the lowercase m indicates, is 75 kilograms. I plug in a positive 9.8 meters per second squared because I have no vector symbol there. Then I divide that by 1/2 the mass of the cylinder, which is 225 kilograms, plus the mass of the man. I end up with an acceleration of 3.92 meters per second squared. This number is logical since, as I mentioned at the beginning of this problem, he should not be accelerating at g, 9.8 meters per second squared, because he also has the upward force of tension acting on him. Let's check out part B of this problem. What is the angular acceleration of the cylinder? Well, part B is pretty easy because all we need to do is plug in the acceleration we found and the radius into this angular acceleration equation that you find on the middle of your screen. So for part B, alpha is a over r. A, as we know, is 3.92 meters per second squared. And the radius of the cylinder is 40 centimeters. I know that because the problem tells me the diameter is 80 centimeters, so I divide that by 2. Now, of course, I need to convert that to meters, so instead of 40 centimeters, I plug in 0.4 meters. I find that the angular acceleration is 9.8 radians per second squared. It is simply by coincidence that that is equal, that number 9.8 is the same thing as g. That will not always be the case. Lastly, part C says, well, what about if the mass of the rope were not neglected? What would happen to that angular acceleration of the cylinder? Well, we completely ignored the mass of the rope. It wasn't something that was important to our calculations. But think about it. As the man falls, more and more of the rope has fallen as well, which means that mass increases. If the mass that's falling increases, so will the acceleration. If the acceleration increases, the linear acceleration, so too will the angular acceleration. So eventually, this object will be getting faster and faster. It will not have a constant angular acceleration. Hopefully, these two problems have helped you understand Newton's second law for rotation a little better.